Hello everyone. Today I will present to you our paper Hardware-Aware Pruning of DNNs using LFSR-Generated Pseudo-Random Indices. I'm Foroozan and this work is done at Integrated Circuits and System Research Lab at Georgia Institute of Technology with my advisor Professor Arijit Raychowdhury. Artificial neural networks have shown remarkable performance in a broad range of applications, from computer vision to healthcare data analysis and natural language processing. Ever-increasing number of edge devices such as mobile, wearable devices, and Internet of Things requires computation to be performed on the edge. Recently, deep learning on mobile has attracted a lot of attention due to several advantages. Sending and receiving data from a centralized server like cloud increase both the latency as well as the cost of communication. On the other hand, edge computing can enable real-time data analysis locally, which reduces the latency and increases privacy of the data. It's also important where we need accurate and fast computation to generate results under a strict latency constraint. So we really want DNNs to run locally on mobile and edge devices. But what are the challenges that we face? While DNNs are powerful and provide high accuracy for complex tasks, they cannot be easily deployed on embedded mobile applications due to two major problems. First, because the models are large and often over-parameterized, it must be stored in an external DRAM. The second issue is that accessing model parameters from an external DRAM consumes large amount of energy. For example, in the 45 nanometer CMOS technology, accessing a 32-bit DRAM memory requires 3 orders of magnitude higher energy than a 32-bit floating point add operation. Therefore, it's hard to deploy large DNNs on battery-constrained mobile platforms. Network compression using pruning techniques is one possible solution to fit large DNNs such as VGG16 with 138 million parameters in an on-chip SRAM. A lot of works have been done in the literature dedicating to propose new methods for DNN compression. Some of them are threshold-based methods to prune the connections, which are less than a threshold, while others are use more structure-based approaches such as blockwise pruning. However, it's challenging because sparse matrices add extra level of irregularity to the weight addresses, which adds another level of complexity to the network during inference. The state-of-the-art pruning method, which we use to compare with our method later, prunes the redundant connections in an iterative process based on a threshold in 3 steps, including training, pruning the connections less than a threshold, and retraining. Also, during the inference, for the baseline algorithm, the sparse weight matrix is compressed in 3 vectors: the non-zero values of the weights S, locations of the non-zero weights I, and a pointer vector to point to the start of each column of the weight matrix P. That all of them should be saved in the memory. All in all, these methods are powerful from an algorithm perspective, but its mapping to hardware is inefficient and they are not designed to address the real hardware bottlenecks, and they require to store the locations of unpruned weights, which leads to a memory footprint as high as 2 times higher than the model size. This motivates us to propose a hardware-aware method to prune dense DNNs using LFSR-generated pseudo-random indices, which reduce the memory footprint while preserving the original accuracy. The proposed pruning method consists of 4 steps. It begins with generating a pseudo-random sequence, PRS in short, using 2 LFSRs, one for row indices and another one for column indices. We then use the generated PRS as the indices for the weights that we want to be kept and sparsify the remaining connections, orange blocks in the figures, by using standard regularization methods in an iterative approach. The specified connections are regularized to force them to be zero in the training step. After heavily regularizing the selected weights, a pruning step is employed to make sure that all the selected weights are exactly as zero, as regularization makes the connections very close to zero, but not exactly zero. The last step of the process is to retrain the pruned network for several epochs to fine-tune the remaining connections so that they better compensate for the removed ones. Using a PRS for generating the locations of zero weights in the connectivity matrix makes it easier to generate the indices on the fly instead of being stored in a separate memory subbank. In this slide, I'm going to explain the circuit diagram of the proposed DNN accelerator during inference. The figure shows the hardware resources and operations to solve a sparse fully connected layer with M input neurons, N output neurons, and SP as sparsity. For the hardware implementation of our proposed method, the LFSR is used to generate the index for the input to be multiplied to the corresponding weight value in a sparse weight matrix. LFSR is one of the most commonly used topologies for implementing and generating pseudo-random bit sequences. It consists of an array of flip-flops with an initial state called input seed, followed by linear feedback performed by several XOR gates, CI. LFSR can be mathematically described through nth order primitive polynomial and can be generate the pseudo-random sequence with value between 1 to 2 to n minus 1. N, small n, is the order of polynomial. In order to keep the value between number of input neurons, we multiply the generated value to the length of the input neurons and select the most significant bits, MSBs. The goal is to avoid redundant clock cycles when the generated number is greater than the number of neurons. This process generates row indices for the next step. Let's look at the one example of how the row indices is generated. Let's say we have an LFSR with primitive polynomial equals to x to the power of 9 plus x to the power of 4 plus 1, and the input seeds of 1, 1, 1, 0, 1, 0, 1, 1, 0. Also, the input neurons equals to 300. One of the generated output sequence from the LFSR can be the number 460. However, this value is greater than the number of input neurons. One solution is to skip this number and take the next sequence, but this will cause redundant clock cycles and decrease the performance. To solve this problem, we multiply it to the value of the input neuron, which is 300 in this example, and take the most significant bits. Here, the MSB is equal to number 270. In this way, we bring all the values to the range of the input neurons and prevent redundant clock cycles. And then a row index is generated, which is used to select the right input element. After doing multiplication and accumulation operation, the result is stored in the output buffer. The index comes from the LFSR with different input seed, which is responsible for generating the sequence for output address. The advantages of our proposed method are, first, LFSR can be easily implemented in hardware. The generated random sequence has the key property to preserve the rank of a generated connectivity matrix. The indices of addresses are generated automatically in real time. And finally, we no longer need to store the addresses of a sparse weight matrix. To evaluate our proposed method, first we chose the hyperparameters. 3 different lambda, the regularization parameter, have been tested on the proposed method, and the results before and after retraining are illustrated. The results show that moderate and strong regularization lambda equal to 2 and 10 have better performance before and after retraining. We picked lambda equal to 2 to trade off between pruning and convergence of loss function while preserving overfitting. In another experiment, we used both L1 and L2 regularization as the regularization criteria. L1 has better performance before retraining, while L2 achieves better performance after retraining. And then we chose L2 for our pruning method. It should be mentioned that we mainly focused on pruning fully connected weights as they consume the maximum amount of memory resources, and we observed that our method does not affect the rank of weight matrices during pruning. As a matter of fact, the rank is in the proposed approach is close to 4 rank as in unpruned model of the dense matrix. Since the PRS maintained the matrix rank, we inferred that the expressibility of the weight matrices and accuracy of the network can be remain unchanged. The proposed methodology is demonstrated on 3 pruned network, LeNet 300-100, LeNet 5, and VGG16 using MNIST, CIFAR10, and downsampled ImageNet datasets. Rate of compression before and after pruning for 3 mentioned models are shown in the table. We demonstrated that our model can prune LeNet 300-100 11 times, LeNet 5 10 times, and VGG16 by 7 times with no accuracy loss. Also, we compared the accuracy of our method with the baseline method in different sparsity rates. The mean and standard deviation accuracy of proposed and the baseline method for 5 trials are illustrated in the figure. The results show that our method is reliable and can preserve the accuracy even in more complex networks such as VGG16. We have synthesized the baseline and our method with 65 nanometer CMOS technology to measure hardware metrics. The pre-layout analysis demonstrates 1.5 times to 2.94 times reduction in required memory footprint of overall system between proposed method and 4 to 8-bit indexed baseline pruning technique. In summary, not only LFSR-based pruning method is powerful from an algorithm perspective, but also its mapping to hardware is more efficient and requires much less memory footprint than the baseline pruning method. Besides memory, the overall system parameters are also measured. The power and area measurements are demonstrated in Table 1 and Table 2. We observed that a maximum of 63% power saving and 68% area saving across varying sparsity indexing, bit width, and baseline design. In conclusion, we present a hardware-aware pruning method where the locations of non-zero weights are derived in real time from a linear feedback shift register. This is a new method of indexing to use a sparse network for inference to enhance the memory usage and energy efficiency of DNNs. Therefore, we no longer need to store the addresses and we can generate them automatically during the inference. Our method can prune large networks without loss of accuracy, and the maximum of 63% power saving and 68% area saving can be achieved. And finally, we can make DNNs deployable on mobile applications. Thank you.